Hey guys, welcome back. Today we're doing the DC analysis of a PNP BJT. So how do we know this is a PNP? Well, we see that the arrow in the transistor emitter is pointing into the transistor. That's how we signify it's a PNP. If it was a NPN, the arrow would be pointing outwards. So what we're going to do in this analysis is we're going to find the current voltages in the base, collector, and emitter. And we're also going to solve for the DC parameters, GM and RPi. Also, quickly to note, VT and beta in any transistor is always going to be equal to VT 25 millivolts, and beta will always be equal to 100. It doesn't change from transistor to transistor, it's always going to be the same. So let's start off with the DC analysis, shall we? So since we know it's a PNP, the first thing that we have to write down is we know that VEB is going to be equal to 0.7 volts. If this was an NPN, it'd be VBE equals 0.7. Now, what does this mean? Well, VEB actually signifies the voltage drop or difference between VE and VB. So now that we have this formula, we can simply just find equations of VE and VB and make it in terms of one variable. So as we can see here, VE, we can see from the circuit, VE would be equal to 15 minus the voltage drop at the resistance, which is going to be minus 9 times IE. And now for VB, it's a little more complicated. We have a more complex circuit on that side. So we can simply write a KCL at node VB. So what we get from doing KCL is 15 minus VB over 3 ohms plus IB. Now in the NPN, we had minus IB, but that's because when you have a PNP, the current in the base is the opposite way as an NPN, where the current in the base in a PNP goes outwards, while in the NPN, the current goes into the transistor. That's also something extremely important to note. And so these two currents will be equal to the current flowing through the 9 ohm resistance. Now we can write this as VB over 9. So now that we have this formula, we can see that we can solve for VB by isolating VB on one side and keeping everything else on the rest. So we can simply write this as VB 1 over 9 plus 1 over 3, since this is what the factored out version would be, equals IB plus 5. Now if we divide both sides by everything that's in this bracket here, we get VB equals 11.25 plus 2.25 IB. So now that we see we have two equations, we'll name VE equation 1 and VB equation 2. We see they're in terms of IE and IB, but we know that given any current in a transistor, we can make it into a function of another current. So for example, we can change IE, knowing that IE equals beta plus 1 IB. We can write this as 15 minus 9 times beta plus 1 IB equals VE. We'll name this equation 3. And remember, beta is always equal to 100, so this is basically just saying 15 minus 909 IB. So now that we have these two formulas, we can combine 3 and 2 into our original formula, which I'll underline right here. This is our original formula. We can combine 3 and 2 into our original. So once we combine 3 and 2 into our original, we simply get 0.7 equals 3 minus 2. So we can write this as 0.7 equals 15 minus 9 beta plus 1 IB minus 11.25 minus 2.25 IB. Now, simply, we see we can just solve easily for what IB is. And in this case, when we isolate both sides, we get IB negative 911.25 equals negative 3.05 once we bring everything to their respective sides. And from this, we can find that IB, if we divide both sides by negative 911.25, we get IB equals 0.33 milliamps. Or, my bad, sorry about that, 3.3 milliamps. So now that we have IB, we know that we can find IC by multiplying IB by beta. So we can simply multiply IB by 100 to get IC. And what we end up with when we multiply IB by 100 is 0.33 amps. And now IE is equal to beta plus 1 IB. Remember, you guys should all know these equations. They're extremely important. You should know them off the top of your head. IE equals beta plus 1 IB. That gives us 0.34 amps. So now that we have all the currents, we can simply solve for the voltages now. So using the currents that we found, we know that VE is equal to whatever the voltage is at the source minus the voltage drop at the resistance. So it would be 15 minus 9 IE, which we found IE to be equal to 0.34. So this simply gives us a voltage at VE of 11.94 volts. Now we can find VC. VC is the easiest one here. It's simply just the voltage across the 3 ohm resistance. I'm so sorry, that should be a 3 ohm. We get 3 multiplied by IC. And this simply gives us 0.99 volts. Because IC, remember, was 0.33. And now for VB, we found an equation from doing the KCL that we performed. That was simply 11.25 plus 2.25 IB. Now, this was found from the KCL that we did before. And once we plug in IB, we simply get 11.26 volts. Now, to determine if these are active, remember, the currents we found must be positive. Now, were they all positive? Yes, they were. Check. And the second condition is that VB has to be greater than VC. Clearly here, we can see that VB is 11.26, which is much greater than VC, which is only approximately 1. So yes, we know that this transistor is going to be in the active mode. Now we can simply solve for our DC parameters. So GM equals IC over VT. Now remember, VT is always 25 millivolts, so IC, what we found, was 0.33 amps divided by 25 times 10 to the negative 3 volts. Now this will simply give us 13.2 ohm to the power of negative 1. And then now we can find our RPi value for our small signal analysis, which is beta over GM. Now we know beta is always equal to 100, and GM was equal to 13.2 ohm to the power of negative 1. Now this simply just gives us an RPi value of 7.57 ohms. Now, I hope you guys learned something. Thank you so much for watching.